Now that we know what algorithms are and we've seen some examples of algorithms through linear search and bubble sort, we want to talk about how do we define what a good algorithm is. How do I look at an algorithm and say that is a good algorithm? So that's what this video is going to be about. When we start considering what makes a good algorithm, we might be thinking of two different aspects of the algorithm: characteristics or the quality of the algorithm. Now, when it comes to characteristics, we're talking about how well the algorithm is presented. So, is it unambiguous? Does it terminate? Ultimately, does the algorithm work? When we consider the quality of the algorithm, we're considering how well the algorithm actually solves the problem. So for the quality, we might consider how fast does the algorithm solve the problem, or how much memory does it use? And is it accurate? How accurate or how robust is the solution? Now, in this video, I'm going to be focusing on the characteristics. And that's because if we can't present an algorithm in a good way, then that can obscure or mask the quality aspects of an algorithm. So we will come back to the quality because the quality is very important in terms of understanding how efficient your algorithm is. But for now, let's start on writing good algorithms that are well presented, easy to read, and then we'll move into the quality of the algorithm. The best starting point is asking, does the algorithm work? We're not really asking how well it works, just do we get the answer that we desire from all reasonable inputs? We also need to identify and test all the boundary conditions. So if your algorithm isn't testing those boundary conditions that are within our reasonable assumptions, then we can't say that this is a good algorithm. We also need to make sure that all our assumptions are reasonable. There are some assumptions that just aren't practical, would not fit the problem description, and if our algorithm has those, we can't say that the algorithm is a good algorithm because it's not truly solving the problem we want to solve. And then, does it terminate? Does the algorithm run on forever in particular conditions? If it does, clearly that's not a good algorithm, so we need to address those. So that would be the first thing that we want to consider when considering if this algorithm is good is, does it satisfy all the basic conditions of does it work? The next thing we want to consider is the language in which we write the algorithm. We know that algorithms need to be agnostic to any given programming language. And so if we look at an algorithm, we say, oh, that's C++ code, well, then clearly that algorithm isn't appropriate and we didn't write it well. So we want to make sure that we write our algorithms in English or math. Really, it's your natural language, but for the duration of these videos and my courses, we'll always use English, or some type of graphical representation through flowcharts. Now, as a novice computer scientist, when you're first starting to learn these skills, you want to do it on paper. Yeah, there's a lot of cool technology out there for drawing out flowcharts or typing up your algorithms, but it's hard to think in that way. You really want to take pen to paper. Now, if you have a tablet and you're doing it in that form, but you're still writing it out, that's fine. But the habit of putting pen to paper, it's just going to help you understand algorithms a little bit better than typing it out. So I strongly recommend that you don't try to type your algorithms first. You try to draw them out on a whiteboard or on a piece of paper or even on your tablet, and you're going to start getting a better feel for figuring out the problem that you're trying to solve. And then at the end of the day, you can transfer it to written form using your keyboard and your computer. Another important characteristic that we need to consider are inputs and outputs. They need to be extremely well defined because they are what's going to drive us creating our algorithm steps. So in terms of our inputs, they determine kind of the information that is known and any assumptions that we might be making. And without that, we won't know if do we need to check to see if a list is empty or not, or can we just assume that the list has at least one element in it. So the inputs are really going to sketch out the scope of the problem that you're trying to solve. Now, the outputs clearly determine what the form of the solution is going to be. Is it going to be a list that we're returning? Is it going to be true or false? And again, understanding this is going to lead us into what the solution is actually going to look like. Another key aspect of a good algorithm is that it's clearly written. So there should not be anything that's ambiguous. No matter who reads your algorithm, they should have the same understanding. So if person A reads the algorithm and says, oh, this algorithm is trying to find the largest element in the list, then person B should also have that same understanding. But not just what the overall gist of your algorithm is, they should understand every single step and how you plan from getting from your inputs to your outputs. And if any two people come up with something different through reviewing your algorithm, then you know you have some issues in the way you've presented your algorithm. Another thing that kind of ties into this same conversation is all your instructions need to be precise. You can't skip anything. If you jump from point A to point C without going through B, there's going to be a chance that somebody can interpret your algorithm differently than you intended. So you need to make sure that every little step of your algorithm leading you to your solution is well presented. Now let's take a look at the find max algorithm that we brought up in a previous video and go through asking ourselves, is this a good algorithm in terms of its characteristics? So just as a reminder what this algorithm is, we're given a list of positive numbers and we want to return the largest number in the list. So we have our inputs that are an unordered list L of n positive numbers where n is greater than 0. And we have our output, which is max, and it will denote the maximum value in the list. So the way we decided to solve this problem was we set max to be 0, knowing that since we have positive numbers, that no value can be less than that. And so for every element in that list, we want to check to see if the element is greater than max. If it is, we update the new max to match that element. If not, we just go to the next element, and we continue till we get to the end of L, and we've checked all n numbers, and then we return whatever max is. So that's our algorithm. And in the previous video, we already proved that it works. But now we want to ask, is it a good algorithm? So let's pull up the checklist of things that define what a good algorithm are or is in terms of characteristics. So does it work? Well, yes, we went through it and we scratched it out on paper and we said, yes, this algorithm does work. Is it agnostic to any given programming language? Well, if you look at this, it kind of looks like a programming language, but you couldn't tell me that it's C++ or Python or Java. It's pseudocode that we wrote it in, so it is agnostic to any given programming language. Is the input clearly defined? Is the output clearly defined? Yes, it is. Right under the problem statement, we have exactly what our input is with variables, and we have exactly what our output is. So that's good. Is it unambiguous? So first of all, the inputs and the outputs, we understand what those are. It makes sense. If we go through each step, 1, 2, and 3, there's really nothing in there that's confusing. There's only one way that you can really interpret each of those lines. And so, yes, I do agree that it's unambiguous. Is it precise? Is it well written? Yes, it is. There's nothing here that's going to confuse us. Did we skip any steps? No, we're going through each element. Every step is well defined. There's nowhere that I have to make an assumption or I have to guess what the implementer or the algorithm designer was thinking. So again, I would say that this is precise. So for each algorithm that you write in my courses or just in general, you should have this checklist next to you and ask yourself, does it work? Is it agnostic? Are the inputs and outputs clearly defined? Is it unambiguous and precise? And until you can honestly say yes, 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 all the way down, keep working on your algorithm. Keep focusing on what are the issues. And then that's how you're going to start developing your algorithmic skills.